Hello, I completely forgot to record my second period class today, so here I am recording during some lesson plan time over in my STEM lab. Here we go. I need to share my screen. Tab, share that screen and present. Okay, so we are going to finish up chapter 4 today. We'll be in the final section, section C, talking about periodic trends. All right, the objectives of this lesson. Number 1, why is the periodic table shaped the way it is? Number 2, is there an easy way to show elements and their electrons? The answer is yes. Number 3, how does an element's position on the table relate to its properties? We already know a little bit about this because of the things we've been learning in the first 2 sections, but there should be a little bit of new information for you today. First of all, why is the periodic table such an odd shape? Well, it's based off of how many protons and electrons are in an atom, okay? So it's related to the structure of the atoms themselves. So we know, we've already covered that every horizontal row in the periodic table has a different number of energy levels or electron rings. Okay, we also know if we organize the periodic table vertically, if we look at the vertical columns, each of those columns has a different number of valence electrons, and those are the electrons that exist in that outermost energy level, okay? So let's take, for example, oxygen. We've got oxygen, which is located to the right of that metalloid stair step. The metalloid stair step is what separates the metals on this side of the periodic table. Let me get my laser pointer here. We've got the metalloid stair step right here, and it separates the metals on this side of the table with the non-metals on this side. Okay, so oxygen is a non-metal. Its atomic number is 8, which tells me it has 8 protons. Its atomic mass is 16, even. It doesn't have any decimal points. So we know that oxygen 16, with a mass of exactly 16, is the most common isotope. And we know we can calculate the number of neutrons by subtracting the protons from the atomic mass to equal 8 neutrons. So oxygen exists in its most common state, in its most common isotope, with 8 protons, 8 neutrons, and 8 electrons. Oxygen is in the 16th column. If we count every single column on the periodic table, it's in the 16th one. We know that it also has 6 valence electrons because when we count valence electron groups, we ignore all the transition metals in the middle because all of those have between 1 and 2 valence electrons. So we count the first 2 columns of the alkali metals and the alkaline earth metals. And then we jump on over here. We start at boron. We have 3, 4, 5, 6. And we know that fluorine has 7 valence electrons. In this last row, these noble gases have 8 valence electrons, the ultimate level of stability, okay? That's what every element wants to be at. All right, it's in the second row, which tells me it has 2 energy levels. So those 6 valence electrons are located in the second energy level, the second energy ring, okay? So electron dot notation is an easy way for us to represent how many valence electrons are in an element. This is kind of a convoluted definition. It says a representation of an element's ability to attract and hold electrons when bonded to other atoms. So an easier way to remember this is if you see an element symbol with dots around it, it shows you how many valence electrons that specific element has. Here's an example of electron dot notation. This is actually a bad example. This is a graphic from your book. So electrons actually fill these empty spaces, these energy levels, in a different way than this. Well, I'll explain in a moment. So as we move from left to right on the periodic table, we add valence electrons, okay? So this is showing column 1, group 1, has 1 valence electron. Group 2, each element has 2 valence electrons. Group 3, each of these has 3 valence electrons, okay? So the interesting thing about this specific graphic is that electrons actually fill in these energy levels the way people fill in a bus, okay? You're gonna get on a bus and you're not gonna sit by a stranger if there's open seats available, okay? You're gonna go to that first open seat unless you're a crazy person that wants to socialize with other people on a bus. You are very dissimilar to me. So valence electrons fill energy levels like people fill in a bus. They come in, and they fill in the empty seat first. So this electron right here would actually be on top. So beryllium would have one here, and then one on top, and then one on the right. I guess it doesn't really matter its exact location, but just note that they fill in one at a time, and then once all those spots are full, then they start doubling up, okay? When you're talking about electron dot notation. So as we move from left to right, we add valence electrons until we reach the epitome of stability, the noble gases who have 8, 2, 4, 6, 8 valence electrons in their outermost energy level. As we move from top to bottom on the periodic table, we add energy levels. So elements in row 1 have 1 energy level. So hydrogen's 1 electron is in its 1 energy level. It's pretty simple. Lithium's 1 valence electron is in its 2nd energy level because it's in row 2. Sodium's 1 valence electron is located in its 3rd energy level or 3rd electron ring because it's in the 3rd row. This will hopefully make more sense when we get to the element builder gizmo. Atomic radius is another way that we can organize the periodic table. Atomic radius is the distance between the center of an atom's nucleus and its outermost energy level. So let's put on our critical thinking hats and think to ourselves, if an atom has more energy levels, so as we move from top to bottom on the periodic table and add energy levels, atomic radius is going to increase because this distance is going to be longer if we have to reach energy levels that are further out, okay? So the more energy levels an atom has, the larger its atomic radius is going to be. So that tells us that as we move from top to bottom, atomic radius should increase, in which it does. Okay, what's curious about atomic radius though, is as we add valence electrons, you see what happens? It gets smaller. And the reason is because that positively charged nucleus where all those protons are is going to have a stronger pull on those electrons. So as we add valence electrons, there's going to be a stronger pull and it's going to pull them in closer and make that atom look smaller. Okay, so atomic radius increases as we move from right to left. So as we decrease valence electrons and as we increase atomic radius. So, or as we increase energy levels. So atomic radius increases as we move from right to left and top to bottom. Electronegativity is another way to classify the periodic table, and it's the exact opposite of atomic radius. So I like to think about this. Electronegativity is the measure of an element's ability to attract and hold electrons when bonded to other atoms. So I like to think about this, and this helped me when I was taking chemistry in college, is to think about the difference between 2 extremely fat people hugging and 2 extremely skinny people hugging, okay? That might not be socially appropriate nowadays, but it helps me with the visual, okay? So you've got 2 extremely large, so if we go back, you'll see like francium. The francium atoms have a large atomic radius. Think about those as like really fat people, and they're trying to hug each other, okay? Their arms aren't long enough to really get a good hold, so they could be easily broken apart, okay? So if you've got a small atom like fluorine, super duper skinny people, they can hold on to each other tighter because they're not trying to reach around their large bellies, okay? All right, they have a stronger attraction to other atoms when they're bonded together. So electronegativity increases the exact opposite of atomic radius. It increases as we go from bottom to top and left to right. It increases because of the strong attraction exerted on the electrons by the nucleus. All right, so that's all I had for the lecture today, but we're going to move on to this element builder gizmo. If you click on this, it's a hyperlink. It'll bring you to this. Let me go ahead and I will share the other screen. Stop presenting. Let's present a different tab. Share. Actually, I'm going to share my whole screen. Stop presenting. Share my entire screen. Okay. Okay, why do I not have permission to share my entire screen? Okay, one moment.